major discovery that was made earlier this year, before we get on with the rest of the show. This photograph shows you our Mark II telescope down at the bottom end of the site here, with a lovely rainbow over the top of it. And the rainbow's the sort of the visible light, but you know there's all radio waves, X-rays, gamma rays, all these things are different parts of the electromagnetic spectrum. But it's not the only way we can study the universe. And one of the amazing things that we have been looking at recently, I think it's called gravitational waves. So it's something Einstein predicted back in the early part of the 20th century. And what this video shows you is two black holes orbiting one another, and what you see underneath them is the curvature of space-time. So the mass of the black holes causes those sorts of dips. And if you can imagine, if you can see those, black holes rotating around each other, then what happens is you get ripples in space-time that travel out from the black holes through the universe. And as the energy is carried away in those gravitational waves, then you actually end up with a burst of ripples that spread out through the universe. This is just slowed down now as those black holes merge together. You see this big burst of gravitational waves spreading out that sort of set off through space-time. Those things that spread out through the universe then eventually reach us. So even if this happened maybe billions of years ago, those ripples actually come through us. Billions of years later, you see the ripples spreading out, and the effect that it has is to do this. So what it does is it actually stretches you and squashes you. So all the time these things are happening way out in the universe, there's these sort of little ripples flowing through us all the time, and they're stretching us, and then they're squashing us all the time in this flood of different gravitational waves passing through us. And you've come to Jodrell Bank for a music festival, but you shouldn't avoid being forced to look at an equation. I'm very pleased that you're happy to see an equation. This is Einstein's equation for gravitational waves. What is it? That's the fractional change in length, delta L over L. So if I was like 2 meters high, which I'm not, then that'd be my length L, and then the change is the delta L. So it's sort of like a 1% change, that number would be 0.01. And on the rest of the equation, what you've got is the size of the black hole, the distance it is away from you, and the speed at which those black holes are moving. And that tells you how much of a squashing and a stretching that you get. The trouble is, when this happens, the squashing and the stretching that you get is not 1%, so it wouldn't be changing your 2 meter height by 2 centimeters, which would be 1%. It's changing it by 0.20 zeros and a 1. So it's an incredibly tiny change in the sort of size of things as these things arrive. But we've actually detected them, and we've detected them with gravitational wave observatories earlier this year, one of the most monumental discoveries in astronomy of recent years. And very nicely, we have one of the astronomers at the Gravitational Wave Observatory in Louisiana is hopefully on the end of a Skype line. It's Dr. Stuart Aston, who...
Hello, Tim. Hello, Jodrell Bank. Welcome to the LIGO Livingston control room. And this is the hub of where we control access to the site. We can control most aspects of the detector from here, and we also monitor a lot of information, the interferometer itself, and all of the environmental channels, and seismic activity. And we also have cameras that are spotted around looking at different parts of the laser and the detector. And you might notice from, I hope Tim has got an image there of the site, is that there's some very distinctive 4 kilometer long arms. It's a very distinctive L shape, and these house a very large vacuum system. So it's one of the largest vacuum systems actually in the world, and the idea is that basically there's nothing inside of these beam tubes. We evacuate all the particles that we can, and the laser beam propagates through these beam tubes, and the arms are 4 kilometers long, and we have to take account of even the curvature of the Earth when we were laying the foundations for these arms, because over 4 kilometers you have to take account of a meter rise in the end stations. So there's 2 arms, and that's so that we can be sensitive to these gravitational waves, because as Tim mentioned, they're usually stretching in one axis and squashing in the other axis. So this helps improve the sensitivity of the interferometer.
Can you hear me there, Stuart? Can you hear
Yes.
me? Yeah, could you just tell us, I mean, you meant those screens behind you, what are the things, given that it's such a tiny change, what do you have to worry about that could confuse the results?
There are many factors that we have to worry about. So the idea is that the mirrors should be just completely isolated from everything. So the only perturbation that can affect them, ideally, should be the gravitational waves. But unfortunately, there's wind and acoustic noise. So this is why we put them inside of large vacuum chambers. And the other major contributor is seismic noise. So we have to be very, very, very. We have to develop technologies to help isolate these mirrors from the motion that we have on the ground. And the ground is moving all the time at different rates. So there's the sort of standard issue is with waves on the coast. As they hit the beach, they sort of usually hit with around about 7 seconds between each wave. We also have to try and isolate it from slower motions from earthquakes, and obviously at higher rates from human activity, such as interstate, people, cars, planes, railways and trains. So we use sort of a technique called a pendulum. I can demonstrate it here with a yo-yo, actually, to try and demonstrate how we use a pendulum to isolate the test mass. So if this is the mirror, you can see that very slow motions of the ground. The mirror is basically following the ground motion. But if I was to move the ground a little bit faster, hopefully you can see that the mirror in that case is actually isolated from the ground motion fairly well. And so we sort of make most use of this effect. So we actually have not just one pendulum to isolate the test mass, we actually have 4 pendulums. And this eventually affords us around 12 orders of magnitude of isolation from ground motion for the...
That's a million times isolated from all the motions. How far away are these waves? Can you hear me there? Internet connection to Louisiana. Oh no. We can detect gravitational waves from the merger of black holes a billion light years away, but we can't connect to Louisiana on Skype. I think we might give it a break. Actually, sadly, we've lost Stuart. I think so. We'll oh.
Hiya, mate.
Stuart.
We're at a remote observatory. The Wi-Fi connection is not that stable.
Stuart, we're losing. I think we're losing the internet connection too, so we're going to have to cut this short, I'm afraid. But before we go, I want to thank you for giving up some of your Sunday to talk to us, and I think everybody can thank you as well. And if you next time you detect some black holes merging, can you tell us about it?
Absolutely, yeah.
Cheers. Thank you very much. See you later. So sorry about that. That was a little bit problematic there at the end, but I hope you heard a little bit about that. If you go and look up LIGO, L-I-G-O, one of the most amazing discoveries we've been able to make, to see these sort of ripples in space-time. If you fancy some exercise later, remember what you've got to do is stretch and squash. Right, stretch and squash. So we'll be doing that later. I can see there's a gentleman at the front's very keen, but for now, thank you very much, and we'll move on with the rest of the show.